I am Ratilal from second year MTech Photonics at IIT Roorkee. Today I am going to talk about pulse broadening in photonic crystal fiber due to self-phase modulation. In that we introduced femtosecond pulse in photonic crystal fiber and we saw the pulse broadening due to self-phase modulation. Let's begin with motivation. Here we can see the input femtosecond pulse in temporal domain and we get the spectral broadening in frequency domain. This spectral broadening is useful for the ultra fast switching in optical fiber. This phenomena, self-phase modulation phenomena, is also useful in to generate supercontinuum, which is useful for the to make a broadband wavelength source. SPM create new frequency by transferring optical power. Here is the outline of the presentation. Introduction, self-phase modulation in photonic crystal fibers, MATLAB simulation results and references. Here is the introduction of the presentation. The nonlinear Schrodinger equation, which is the main base of our simulation result. This after solving this differential equation, we get our simulation results. Here is A is envelope of the pulse, input pulse. Alpha is the loss coefficient of the fiber. Beta 2 is GVD parameter, that is group velocity dispersion parameter, which tells about how pulse broad how the pulse get broadens in dispersive medium. That's different components of light travels with different velocities. Gamma is a nonlinear parameter. Here we are interested only in this term, third term, that's nonlinear term. This is GVD term, this is attenuation term. We are interested only in gamma term because we want to see only pure SPM, that is pure self-phase modulation phenomena. The beta 2 and alpha we are not interested because the fiber length is very small, the loss is very low, that's why we are not neglecting this term. And beta 2, the length of the fiber, the non dispersion length of the fiber is very long, that will be not able to see the dispersive way. We are interested only in non-linear effect. Okay, here is the photonic crystal fiber. This is solid core photonic crystal fiber. The black spots are the air capillaries. The distance between two air holes is called as a pitch. The reason behind the using photonic crystal fiber is on highly nonlinear fiber than the conventional fiber. The self-phase modulation, as name suggests, it modulates its phase by own. The light traveling in a highly nonlinear medium, that's interaction cause the self-phase modulation. The refractive index depends on the optical intensity, that's a Kerr effect. N is equal to N naught plus N2I, where N naught is a linear refractive index, N2 is non-linear refractive index. Intensity depends leads to nonlinear phase shift. The introducing of the new frequency is depends only on the nonlinear phase shift. Omega is equal to del phi by del t. That's introduce the new frequencies by varying the length and varying intensities. An optical field modifies its own phase, as we already talked about. Phase shift varies with time for pulse. As time increases, means as the distance of the fiber is increases, the phase will also get increases. Each optical pulse becomes chirp. Chirp, that perturbation introduced in a fiber that's caused the so, pulse broadening and introducing new pulse that causes chirp. Nonlinear phase shift. The pulse propagation governed by nonlinear Schrodinger equation. Here we are not interested in beta 2, we already told, because the beta 2 gives the dispersive effect and here the Here in our experiment, the dispersive length is very high and we are not able to see the dispersive effect. Gamma is a nonlinear parameter. Gamma is equal to 2 pi n2 by lambda, where n2 is a nonlinear refractive index coefficient. Lambda is a central wavelength where dispersive where is dispersion we call as a zero dispersion. If A effective is the effective mode area, if we ignore the dispersive effect, the solution will be written as if we ignore this dispersive effect, we get the solution of this equation. Here is our nonlinear phase shift. To calculate the nonlinear the numerical method, we use the split state Fourier transform method. In our delay by del z is equal to d plus n out of the bracket a, where d is a 0 because we are not interested in the dispersive parameters. We are only interested in nonlinear parameters. The main reason of using split step Fourier transform method to reduce our errors, we divide the uh, fiber in segments with step size h. This alternatively uh, calculate by when n is non-zero, there that time d is 0. That's why that type of thing we can calculate. Here we can get the at distance z, we can get a new envelope, means at a time the what's the condition of the in our input pulse. Self-phase modulation in photonic crystal fiber, the nonlinear coefficient of the conventional fiber is very small, that's way up to 3 per watt per kilometer. But in photonic crystal fiber we get very high nonlinear coefficient. That's why we use a photonic crystal fiber that we get up to the 70 watt per kilometer. That's very useful for the see the spectral broadening or to generate a supercontinuum. Here with the at particular wavelength it shows the zero dispersion length, and that means at that wavelength we get very high dispersion length, and the length of the length of the fiber is approximately equal to nonlinear length. That's why we able to see the nonlinear effects and we not able to see the dispersive effect. The effective mod area is also reduced. In conventional fiber, the effective mod area is very high, generally compared to high. That means here we can talk about the mode field diameter is equal to 2 times beam waist, and effective mode area is equal to pi into beam waist square. That affects the our gamma, because as our effective mode area is very high, the high that reduce the gamma. If the effective mode area is very less, then our gamma is very high. That's why this here we use a photonic crystal fiber as a nonlinear medium. Yes, self-phase modulation induces spectral broadening. As it's traveled the distance, the phase will get changed, and that we introduce the new frequency in our input pulses in frequency domain. As we can see, the it travels the distance affect the phase, and it will get changed in phase and introduce the chirp in that our pulse in frequency domain. Here is the parameters of the photonic crystal fibers. Here is the this SC51040. This is fiber photonic crystal fiber basically used to generate supercontinuum, which is for making broadband coherent light source. Where 1080 is a dispersion wavelength, means zero dispersion wavelength. At that wavelength, that at that particular wavelength, we not getting any dispersion. We can get the different kinds of photonic crystal fiber for the zero wavelength at 800 to 1040 nanometers. The core diameter of this fiber is 1.8 to 4.8 parameters. The different diameters available in this fiber. The material we use to make this fiber is pure silica for core and so for cladding. In this fiber, this structure called the Kagome structure. In that, the air holes are attached very closely. There is no pitch in this fiber. This is solid core fiber, and MFD is quite low as compared to the conventional fiber. This is 4 plus or minus zero point 0.2 micrometers. This is taken from the NKT Photonics. The MATLAB results. The number of these spectral lobes is linearly proportional to the length of the fiber. As we increase the distance, the number of lobes will get linearly increase. We have the investigated the broadening effects for different lengths of fiber. With the single mode fiber 28 is a special kind of single mode fiber, means conventional fiber. We get zero point 0.2 nanometer broadening, but for same length photonic crystal fiber we get 100 nanometers of broadening. You can see the results here. We fix our power at 0.5 kilowatt, and we varies the distance. For 10 centimeter we get 15.6 nanometer broadening. For 50 centimeter we get 83 nanometer wavelength broadening, and for 100 centimeter we get 235 nanometer wavelength. We fix we here we introduced these all things are this spectral domain, and in time domain we introduced this 100 femtosecond pulse, where more results are there. Here we fixed our length of the fiber, and we varies the input power of the pulse. We vary the power the zero point 0.5 kilowatt. We get the broadening of 76 nanometers, and we do for 1 kilowatt we get 146 nanometer broadening. We fix 1.5 kilowatt power, and we get broadening of 240 nanometers. Here we do it different, and the input pulse remains phase same, that's a 100 femtosecond pulse inside optical fiber. Is the conclusion. uh, Due to highly nonlinear photonic crystal fiber we get a spectral broadening in the input pulse due to self-phase modulation. As we increase the input power of the pulse, the broadening also get increases linearly. The phenomena of the spectral broadening responsive for the generating multiple coherent pulses, and that are used to wavelength division multiplexing, as well as in as I already told you, these are multiple pulses are also used in optical switching. The MATLAB software we predicts the spectral broadening in photonic crystal fiber at various distances. Here are the references which I use in my presentations. GP Agrawal's book, the Ghatak Tyagarajan's book, these papers. Thank you for watching this presentation.